Hello there guys, how's it going? Mike coming back at you here with another video on Calculus 1. In the previous video, we looked at some sample problems on the use of L'Hopital's rule to find some limits of some ugly looking things. Today we're going to get into a real life application of Calculus 1. Yes, we actually use this stuff in the real world somewhere. This is a video about one example of where we use this stuff. So think back all the way to chapter 1 in our course, where we talked about the concept of local min and local maxes, and how those things related to the derivative f prime, and then also into chapter 2 as to how we found the local min and the local max for functions. So this technique, this process of we differentiate, we set equal to 0, we solve for x, we do some test values, plug things in, and from there we figure out local mins versus local maxes. This technique has a real life purpose. We want to be able to work with and be able to find the value that's going to minimize or maximize something. For example, perhaps you have to maximize the output that you're going to get from some kind of machine, given some particular constraints, or given some things that have to happen. So this is what we're going to be doing in these kinds of problems. We're going to minimize or maximize a particular quantity given certain conditions that have to be met. And these types of problems where we have to minimize or maximize a certain quantity given certain restrictions, these are called optimization problems. Now, there's a 6-step process that you go through to solve any kind of optimization problem. So we kick it off with step number 1, which is to draw a picture if you can. Many times when you're given your optimization problem, which is going to be a word problem, you can sketch a picture of it, and you can label things and make notes. Sometimes, though, it's not necessarily something that's really practical. Sometimes it's not really the type of thing that you can do. So if you can, draw a picture of the situation that your problem is describing and label things. It's really going to help things become a lot clearer. Step 2, you're going to write 2 equations, your objective equation and your constraint. The objective equation is the equation that describes the quantity you wish to minimize or maximize. So when the problem is given to you, you'll be given some information about the situation that you're in, and the problem might say find the largest possible, say, area or volume, or find the dimensions that will minimize the cost of this, or minimize the surface area, or something like that. So that is what our objective equation is going to be. In many cases, what you're trying to minimize or maximize is some quantity that has a known formula out there, like area or volume or surface area or cost, something like that. The other equation, your constraint equation, is the equation that describes the condition that you are being held to in this problem. We are going to see some problems where we have to put up a border on a certain shaped piece of land, and we only have a fixed quantity of money with which to purchase and put up all this, to put up our border. Or it could be that Another problem that we'll see is that you have a certain fixed amount of cardboard or metal or whatever to create some kind of shape. So that's the equation that you have to, or that your conditions tell you that you have to hold to. Now, this is the most important step out of all 6 steps of our process. It is very, very, very important that you come up with the correct objective and constraint equations. If you don't come up with the correct objective and constraint equations, then the rest of the problem will just crumble. Another thing that you should keep in mind, your objective equation is going to be in terms of 2 unknowns, typically x and y, and that's going to equal some letter. That is going to be a function. Your constraint equation is always going to be something involving your 2 unknowns being equal to some number. It's always going to equal some finite quantity. So constraint, something with 2 unknowns equals a number. The objective equation, something with 2 unknowns equals a letter. So very, very important to keep in mind there. Step 3, once you have your objective and constraint equations, this is where we start to get into the actual calculus-y type of work with these problems. What you're going to do is you're going to take your constraint equation and you're going to solve it for one unknown in terms of the other. It doesn't matter which one you do technically, but based on the problem that you're given, you may find that it's easier or perhaps only possible to solve for one particular unknown in terms of the other. Once you've done this, you're going to take that result, which you just found, and you're going to substitute it into your objective equation. And when you do this, you are no longer going to have an objective equation in terms of 2 unknowns. Your objective equation will now be in terms of 1 unknown. And since it's in terms of just 1 unknown, we can now do some work with that guy. We are armed with the knowledge and the tools of calculus to help us work with this guy here. Step 4, once you have your objective as a function of 1 variable, you are going to take the derivative of that guy. You're going to set it equal to 0, and you're going to solve for the unknown that you have. Again, we differentiate and we set equal to 0 because we want to find the values of our unknown that make our derivative equal to 0, which is stationary points or possible local mins, local maxes of our given function. So once you've solved for your first unknown, for any problem that you're going to see from me, you'll then take this value that you found and substitute it back into your constraint equation. Once you make that substitution, you can solve for the other unknown value that you have. And then lastly, part 6, answer the question you were asked. The question may not necessarily just be asking for what are the values of x and y. The question may say what is the maximum volume that we can have, or what is the cost, or what is this smallest cost. So actually answer the question that you're given. Don't just stop at saying what the unknowns are. So we're going to start off, we'll do one sample problem next, and then in the next video, we're going to do a couple more sample problems, which are a little bit more involved, a little bit more complicated, but still these are optimization problems. And in this video, we're going to do sort of the classic standard first problem in optimization. So suppose a farmer wants to enclose a rectangular plot of land and has $1,000 to spend on fencing. If the fencing on the north and south sides of this rectangular plot costs $10 per foot, and the fencing on the east and west sides of this plot costs $2 per foot, then what is the maximum area that we can close in to this that we can close in with this fencing that we're going to spend? So step one, draw a picture. This is one such case where we can indeed draw a picture here. So here's my rectangular plot of land. X on the bottom, and thus also on the north side, and then Y on the east and west sides. So we were asked in our question, if we go back, the question says, what is the maximum area that we can close in? Those two words there, maximum area, those right there are our key words to say that what we're trying to minimize or maximize, obviously, is the area. And this is going to be our objective equation, which for short, I'll just write OBJ. So we know what we're trying to minimize or maximize. We're trying to maximize the area of this guy. We need the constraint equation. And if we go back to the statement of our question once more, this is where the other information that we were given in our problem is going to come into play. We're told that the fencing on the north and south sides costs $10 per foot, and the fencing on the east and west sides costs $2 per foot. And in total, we have $1,000 to spend on fencing. So if I look at this rectangular plot of land here, if I just look at the north side of this guy here, well, the north side of this rectangular plot of land is going to be X feet long. The cost of the fencing on the north side is $5 per foot. So what is the cost going to be for fencing for that entire north side? Well, it's going to be the cost per foot times the number of feet. So cost, in this case, is going to be 5x. And since the cost on the north side per foot was the same as the cost on the south side, and my apologies, it's $10 per foot on north and south sides. So cost is going to be 10x. The cost for the south side of this rectangular plot of land is going to be $10x as well. We were told that the fencing on the east and west sides costs $2 per foot. So each of the east and west sides is Y feet long. It's $2 per foot. So the cost to Y and 2y. So we figured out the cost for each of the four sides of our rectangular plot of land, and we know that in total we have $1,000 to spend on fencing for all four sides. So I can add these guys up, and this has to equal $1,000. So you have 10x plus 10x, or 20x, plus 2y plus 2y, or 4y. So we come to our objective and constraint equations. The objective, we wanted to maximize the area. Area of a rectangle is simply length times width, or x times y. And then we just went into detail as to how do we solve as to how do we come up with our constraint equation. So next step, once we have our objective and constraint equations, and once again, this is the critical piece to solving any optimization problems. Coming up with these guys correctly is the key piece. If you get these things switched, or if you just jumble what we're looking for up with something else, the rest of the problem is going to fall apart and you're going to be in some trouble. So once we have these equations, take your constraint equation, solve for one variable in terms of the other. It does not matter which one you do, but I look at these numbers here and I see that in the end, it's going to look nicer if I get y in terms of x. So if I subtract 20x from both sides, and then if I divide both sides by 4, that's going to give me y is equal to 250 minus 2x. I'm going to take this result and I'm going to substitute into my objective equation. This whole thing right here is equal to y. So I'm going to take this thing and substitute it in for y in my objective equation. And when we do that, it becomes area, which was x times y, is now x times the quantity, 250 minus 5x, and this is 250x minus 5x squared. I now have that equation, that objective equation, that thing I want to maximize, all in terms of one variable. I can now use my tools from calculus to figure out what are the possible x values or value that is going to maximize this thing here. So now that you have substituted in and got your objective equation to be in terms of one variable, you're going to differentiate, set equal to 0, and solve. The derivative of a, pretty straightforward there, just a polynomial. You get 250 minus 10x. Set it equal to 0 and solve for x. 250 minus 10x is equal to 0, or x is equal to 25. So this is one value that we need. We want to start this guy. We want to save this guy. We're going to need that guy later on. Once you've solved for your first unknown, you're going to take this result, substitute it into your constraint equation, and then solve for your other unknown. So our constraint equation was 1,000 equals 20x plus 4y. Substitute in 25 for x, and you get 1,000 is equal to 500 plus 4y. Subtract the 500 from both sides, and then divide both sides by 4, and you get y is equal to 125. And this is the other piece of information that we needed to help us answer our question. Last step, answer the question that was posed to us. Don't just stop at, oh, x is equal to 25, y is equal to 125, that's it, I'm done, I'm out. One last piece of work to do. Lastly, state what the area was. We were asked what is the maximum area that we can close in. So the maximum area, length times width, x times y, 25 times 125 is 3,125, and the sides were measured in feet, so this is 3,125 square feet. So this is the one sample problem that I wanted to go through in this video with you to see how we're using each of these steps and to go through the full process. Step 1, draw a picture. Step 2, objective and constraint equations. Step 3, take your constraint, solve for one unknown in terms of the other, substitute into your objective equation. Step 4, differentiate, set equal to 0, solve for first unknown. Step 5, take this unknown value, substitute into your constraint, solve for other unknown. And lastly, step 6, answer the question that was asked of you. In the next video, we're going to take a look at a couple more sample problems. These guys will be a little bit more complicated. There's going to be a little bit more work that we have to do, but we're still going to go through this same 6-step process. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy.